everybody. Mr. Covey here, and welcome to AP Calculus BC Summer Video number 4. And today we're going to talk about kind of like after you learned what the first and the second derivative were, really the first kind of application or how you use those, which is you can use them to describe functions. Specifically, what about functions you can describe? I listed some things down here where the function is increasing, decreasing, relative extrema, just means relative mins and relative maxes, concave up, concave down, points of inflection, and then domain is always a good thing to know. It's not directly calculus related. You don't need to know calculus to find domain, but it'll help us to find it as well. We're going to dive right in with an example here. It's going to be kind of fast, so don't forget you can always look back at MAH videos. You did learn this. It was on your second semester final. Or you can always pause if I'm going a little too fast for you. Okay? So we're going to jump in here. Here's our little list of things we're going to find. Here's our function. First, domain. So when you think about domain, it's possible x values. So think about the x values that don't work. Well, you can't divide by 0, so x squared minus 4 can't equal 0. So x doesn't work when, or excuse me, the function doesn't work when x is 2 or negative 2. So if we go to our domain, negative infinity to negative 2. Can't have negative 2, so we need to do a little stop there. Negative 2 to 2. 2 to infinity. You should have in your head that determining where a function is increasing, decreasing, and relative mins, relative maxes, critical points, should all be tied together in your head as having to do with the first derivative. Okay, so I'm going to take my function, I'm going to find the first derivative. I'm not going to use quotient rule, I'm just going to rewrite it like this because I think it'll make our lives a little easier. Okay, I'm going to do my derivative. I'm going to clean it up just because it'll help us down the road. And here is my first derivative. Okay, so there was my original function. Here's my first derivative down here. And the first thing I'm going to do is I'm going to find critical numbers. And those are, you'll remember, when your first derivative is 0 or undefined. When is this fraction equal to 0? Well, when the numerator equals 0, which is at x equals 0. Don't forget to also check where the derivative is undefined. Well, this fraction's undefined when the denominator is 0. Well, that just happens at 2 and negative 2. This is a critical number. Technically, these are not critical numbers because they're not in our domain. So critical numbers do have to be in your domain. Okay? So once you find that critical number at x equals 0, though, how do you use that to help you find increasing, decreasing, and how do you determine whether that's a relative max or a relative min? Is you do something called the first derivative test. You make a little chart here. I call it an increasing, decreasing chart. I really want to emphasize that you should be writing over here that we're doing a first derivative chart to differentiate it from a second derivative chart. Okay? So we're going to throw down 0. We're also going to put negative 2 and 2 because although those are not critical numbers, technically they are still points where our function could change from increasing to decreasing. And we are going to grab some x values in these 4 intervals and plug them into our first derivative. Go ahead and do that real quick. That's what you should get. So then jumping back here, our function is increasing from negative infinity to negative 2. And from negative 2 to 0, I'd like you to separate those because it's not defined at negative 2. And it's decreasing from 0 to 2 and from 2 to infinity. Cool. Jumping back here, remember the idea behind the first derivative test is, our function is going from increasing to decreasing at x equals 0, then x equals 0 must be the top of the hill. It must be a relative max. So at x equals 0, we have a relative max. And if you wanted to write it as a point, you could. The actual point is that. Cool. That all had to do with the first derivative. Now we're going to do some good old stuff with the second derivative, concave up, concave down, points of inflection. I already worked this out, so I'm going to kind of walk through it slowly. If you think you know how to do it, just do it and check. Otherwise, I will walk you through it a little bit here. So it helps to take the cleaned up version of the first derivative. Here I am going to use quotient rule. So low d high less high d low, all of the denominator squared for show. And after I do my quotient rule, I'm just going to clean it up a little bit. Okay, so you can pause if you need to take a look at that. But here is it cleaned up a little bit. And then I'm going to take a GCF of x squared minus 4 and negative 4 out of both of those. Oops, that should be a positive there. Sorry. I'm going to take a GCF out. And I get this. I have an x squared minus 4 on the top and the bottom, so I'm going to cancel. And that x squared minus 4 on the bottom, it's then just going to be cubed. So here is my fully simplified second derivative. Remember, when you look at your second derivative and you want to find possible points of inflection, you set the second derivative equal to 0. So that's what I did. Oops, sorry. That's what I did over here. I set my second derivative equal to 0. Well, that was when the numerator would equal 0. If I'm solving this equation, I get imaginary solutions. We are in BC calculus. We are doing calculus over the real numbers, so nothing dealing with imaginary numbers. So that is no solution. If you think about where the denominator equals 0, that's where the second derivative is undefined. That happens at 2 and negative 2, but remember those are not in our domain, so those do not count as possible points of inflection. So there are no possible points of inflection, but I should still make a little second derivative chart with those 2 points because I could still have a change in concavity there. So I would really like to emphasize that when you make this chart, we're now making a second derivative chart, so you should write that down. Otherwise, the reader can't interpret it. And in this case, it's going to be an AP reader, so we need to be clear. We're going to put negative 2 and 2, and we're going to plug stuff into our second derivative. You should get positive, negative, positive. Okay? So then jumping back here, oops, sorry. Our function was concave up from negative infinity to negative 2, and from 2 to infinity. It's concave down, negative 2 to 2. And although it switched concavity at 2 and negative 2, since those aren't in our domain, those are not counted as points of inflection, so there are no actual points of inflection. Cool. I know that was quick. You need to pause and look back. That's okay. Me and boss Lemke, that's what I'm going to call her, wanted to emphasize something really important to you. So take a look at this chart here. This is a lot of good information you should have in your, oops, I almost closed, have in your brain. So when you think about determining if a function is increasing or decreasing, you should think first derivative. If it's positive, it's increasing. If it's negative, it's decreasing. When you just think about the second derivative, no. My second derivative helps me determine where my function is concave up or concave down. Okay, those things kind of parallel each other. Similarly, when the first derivative is 0 or undefined, well, those are relative mins or relative maxes. Where the second derivative is 0 or undefined, well, those are possible points of inflection. Okay? How do you determine whether a whether a critical number is a min or a max? we did this. We made a sign chart with the first derivative to tell whether it was a relative min or a relative max. Similarly, when you make a sign chart with the second derivative, it helps you determine whether something's actually a point of inflection or not a point of inflection. Okay? I think you guys have that down. Here's the one thing that's really important. Pay attention right now. There's an alternative way to determine whether a critical number is a relative min or relative max, and that is by looking at the second derivative at that critical number. If you have a critical number and the function is concave down, that critical number is a max. If you have a critical number and your function is concave up at that point, it's a relative min. So what you're doing here is doing something with the second derivative to help you classify relative mins and relative maxes. Something with the second derivative jumping over into first derivative stuff. This is called the second derivative test. It is different than this stuff over here, which is just what information the second derivative tells you. Okay, so you should really separate these ideas in your head. The second derivative test for extrema is one thing, and the second derivative in general is just another thing. Second derivative, you should think concave up, concave down, possible points of inflection, blah, 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 blah. Second derivative test for extrema, you should think, if I have a critical number and my function is concave up or concave down, that helps me classify those critical numbers. If your function is concave up at a critical number, that critical number is a min. If your function is concave down at a critical number, that critical number is a max. Again, this is an alternative to a first derivative sign chart, increasing, decreasing chart. That was the first derivative test. This is called the second derivative test for extrema. We'll talk about that again in class, but that's just the point of confusion for a lot of students. All right, moving on. Here's the example I would like you to do. Go ahead and run through that. Same things I want you to find there. Go ahead and pause and check your answers. Or you can watch this video of me playing fetch with Benny, my dog. You should know about Benny if you watched the first video, so if you didn't, go back. But watch this video real quick. I only got her 3 days ago, and she can already fetch that well. It's pretty amazing. Pretty amazing. All right, going back here. Hopefully you checked your answers. Here are the answers you should have got for that. Okay? So 0 was not in the domain. Here's where it's increasing. Here's where it's decreasing. Should have actually gotten relative mins and relative maxes. That was relative max and relative min. Concave up, concave down. And again, the point where in this one where it switched concavity was not in our domain, so it did not count as a point of inflection. Don't forget this should all match up with the graphs. So that first function's graph looks like this. It should match up with all that information we found. That one you just did, here's the graph of that one. It matches up with everything you just said. Here's at -1 is a relative max. Here at 1 is a relative min. You know, it kind of all matches up like that. We're not going to do a lot of graphing. With this type of a problem, we're going to focus more on getting this information, but it's good to think about the graph. And that concludes video number 4. Me and Mrs. Lemke are really excited to see you guys first day of school, and that is all. I'll see you guys later.